All right, welcome to one-sided limits. So today our goals are to evaluate both the right and left side limits and understand the difference between what a value of a function is, overall limit of a function is, and then what a left and right side limit would be. We have looked at this graph before, and we've talked about, different things in this graph. For example, if we look at when x is equal to 0, we know that f of 0 equals 3 because there's a closed circle when x equals 0. But we also know that the limit as x approaches 0 does not exist, because if I were to cover up what actually happens at x equals 0 and try to make a guess about what's going to be my outcome, I can't, because I have two different possible values that could happen. But it's kind of frustrating for us because we know on the left side, it actually looks like we would have an output of 0. And on the right side, it looks like we would have an output of 3. So mathematicians like having lots of different ways of looking at things and lots of different types of data. So we can now use two different ways of describing those limits. We can call it a left side and a right side limit. And we write them in specific ways. So let's talk about what these one-sided limits look like. So our one-sided limit. In order to tell if it's a one-sided limit, we're going to see after whatever we're approaching, there will be a little negative sign or a little plus sign. This just basically means that we are looking at the limit from the left. So this would be our limit from the left side. In other words, we're approaching C from the left. So approaching C from the left. And then the difference is when you see the plus sign, we're going to be approaching C from the right. So our limit is now the limit from the right. In other words, approaching C from the right. All right. So when I look at the left and right side limit, it's helpful because if the left side limit is 2 and the right side limit is also 2, then I know that my limit overall will exist. And that's the only time it can happen. So we can have this limit when x approaches C exist only if L and R are the same. So if L equals R, our limit overall will exist. So our first example, we're just going to go from the graph itself. We have the graph of the square root of x, and we're familiar with this graph. We understand, how it works, and it's one of our families of functions. If I ask you to look at this limit as x approaches 0 from the left, meaning I'm going to cover up everything that's happening on the right side of 0 and try to find my limits. Let me show you what that looks like. So I want you to actually take a piece of paper and cover up the right-hand side of the graph. So starting at 0, cover up everything to the right of 0, because I don't want that to influence my opinion or my thinking. So if I'm looking at as x approaches 0 from the left, well, looking at my graph, there's nothing here. I don't have any way of taking a guess or making an educated guess about what my output will be when my input is 0. So at this point, I would say that this limit does not exist. Okay, there's no way for me to tell what we're going to get when we have an output or an input of 0. So now, if I look at the next limit, which is the limit as x approaches 0 from the right, we can move this little piece of paper and cover up everything on the left side of 0. And now we can start to think, okay, if I'm looking at this graph and I'm saying, all right, what does it look like my output will be when my input is 0? And it actually looks like I'm going to have an output of 0. Okay, I could make that guess without actually knowing what's happening. I would be able to make a pretty good educated guess here. Now, the key is if these two things are not the same, then the limit does not exist overall. So I would say at this point, because the limit from the right side and the limit from the left side are different, my limit does not exist. All right. And then next, let's evaluate the function. So I'm going to actually move this so I can see the graph. Okay. So now I want to evaluate my function. What is the output when the input is 0? And I look at my graph and it's actually 0. Okay, let's move on. Okay, so we'll talk through this one. You've had some practice making a table and using your graphing calculator or Desmos to graph. So I want you to fill in the table and get the graph for this function, and then come back when you're done. I will help you figure out what values you should put in for x in your table. Remember, we're looking at values that are really, really close to whatever C is. So those are the values I would use to the right, or a little bit bigger than C, which is 0. And then I would use these values for the ones that are a little bit smaller than C. Okay, so those are the X values I would use to actually calculate my outputs. So go ahead and pause the video, create your table, create your graph, and then come back and we'll talk about the limits. All right, so you should have something that looks like this. Now, remember, we don't actually care for limits what the output for 0 will be. So I'm not even going to figure that out. I think for most of us, we understand in this particular case, we can't have an input of 0 because then we're dividing by 0. So it actually will be something that's undefined. But our graphs look like this, our table looks like this. And let's talk about the two ways we can now find the left and right side limits. One's from our graph and one's from our table. So let's start by using the table. So if I ask you to find the limit as x approaches 0 from the right side, I don't actually care what's happening on the left side of my table. I'm not concerned. And then I look at my table and I say, okay, as I get closer to 0, what would my guess be for my output? And this is staying constant. So we would actually be able to say, well, it looks like it's going to just be 2. So my guess would be that my limit from the table is just 2. And I'll come back and we'll do this from the graph as well. Now, what if I ask you to find the limit as x approaches 0 from the left using our table? So again, let's move this. And if I look at my table and I'm saying, okay, as I get closer to 0, what does it look like my output is going to be? And again, I could probably guess that my output looks like it's going to be -2. So that's how we can use our table. Now, what if I ask you to use the graph? So again, if I'm asking you to find the limit as x approaches 0 from the right, what if I just cover up everything to the left of 0? Okay, so if I cover up everything to the left of 0, so I can't really tell what's actually happening. And then I say, okay, what am I going to guess my output would be when I actually reach 0? And using my graph, I could say, oh, it looks like my output is going to be 2. And then if I wanted to find the limit as x approaches 0 from the left, I'm going to cover up the right side of the graph. And I'm going to ask myself, okay, what does it look like my output will be? If I had to make an educated guess based on my information in front of me, what would I guess the output would be? And I would say, it looks like my output is going to be -2. So whether we use the graph or the table, we get the same values for our left and right side limits. Now, when it comes to the overall limit, we're going to look at the two numbers we wrote here. Okay, so your questions are they different? If they are, then you say that the overall limit does not exist. So I would just say does not exist. If they were the same, then that would be my limit. So if these were both +2, then I would say, okay, well then my limit is just 2. And then finally, evaluate f of 0. So if I evaluate f of 0, I'm going to go ask myself, when my input is 0, what is my output? Now, we talked a minute ago about how in this particular equation, if my input is 0, immediately I notice I'm going to be dividing by 0. So I would be able to say that this is undefined. Whoops, let me get a pen here. That would be undefined. All right, let's try another one. Okay, once again, I'm going to ask you to go ahead and fill in the table, fill in the graph. I'll help you by getting those values that you would use here. So I would say 1.1, 1.01, 1.001, and then I would say, okay, this would be 0.9, this will be 0.99, this will be 0.999, and once again, we don't care what actually happens when you reach x equals 1. Okay, we're not going to actually evaluate that for this table because we're going to use it to find our limit, not an actual evaluation. Okay, pause the video, figure out, fill in your table, use your graphing calculator or Desmos to graph the function, and then come back and we'll talk about the limits. All right, so here's what you should be seeing. Let's go ahead and find the limit from the graph first this time. So I'm looking at find the limit as x approaches 1 from the left. So I'm going to cover up everything on the left or the right side of the graph because I'm only concerned about what's happening on the left. All right, now as I look at my function and I follow it along and I say, oh, okay, it looks kind of linear. So my guess is that when, let me actually cover up x to the left of x equals, or right of x equals 1, let me do this right here. As I look at my graph and I say, as I get closer to that input of x equals 1, it kind of looks like my graph is going to end up having an output of 3. So using the graph itself, I would be able to see, all right, it looks like my output's going to be 3. Now, let's imagine I want to find the output as x approaches, or I'm sorry, the limit as x approaches 1 from the right. So now I'm going to cover up everything on the left side of 1. And I ask myself again, following the path of this function, when I get to x equals 1, I could probably make a pretty good educated guess that it looks like my output is going to be 3. So using the graph, I get an output of 3. Now I could do the same thing with the table. So if I want to find the limit as we approach x equals 1 from the left, I'm going to cover up the right side of my table and just look at the values in my table as I get closer to 1 from the left. And as I look at those values, they look like they're going to be approaching 3. I can do the same thing to find the limit as we approach x equals 1 from the right. Again, looking at my values in my table, as I get closer to x equals 1, my output values look like they're getting closer to 3. That would be a very good educated guess. So at this point, we've been able to fill in our limits on the left side and our limits on the right side. Now we look at those two limits and we ask ourselves, are those the same number? And if they are, in this case they are, that is what my overall limit is. And I can kind of see that from the graph itself as well. And then finally, I want to evaluate when x equals 1. So if I look at my function, when x equals 1, I have a hole in the graph. So I actually don't have a value when x equals 1. So that would be undefined. And the reason I have an undefined value there is when you go back to your function, your piecewise function, when you're graphing it, there's never a time when x is actually equal to 1. It's either less than or greater than. All right, once again, go ahead and fill in the table, fill in the graph, and come back and check your work, and we'll talk about the limits. All right, so this graph is kind of interesting. It looks a little bit like our reciprocal function, except everything has a positive output. So let's go ahead and evaluate our limits. And we'll do one side of the limit we'll do from the graph and the other we'll do from the table. So let's start by evaluating as x approaches 0 from the left-hand side. That means that I don't care about what's happening on the right side. So let's cover up everything in our table on the right. Now this has an interesting set of outputs. We see that our number continues to grow and it gets larger and larger and larger and larger. If I asked you to take a guess about what you would get when you have an input of 0, it'd be very difficult for you to do that, right? Because that number seems like it's just kind of getting out of control. So in my table, if I didn't know what was happening in the graph, I just had the table, I would say, I can't determine what that limit is. Now, there's two things that we've talked about here. I think Mr. Middleman talked about, you could say the limit does not exist. That's great, okay? But you could also say, you know what, it looks like that number is just growing, growing. So you could say, hey, it kind of looks like it's approaching infinity. Okay, we could say that. And we'll take either one. Now let's say we want to find the limit from the graph. So let's go ahead and do the right side limit. Let's say as x approaches 0 from the right using our graph. So now I'm going to cover up the left side of my graph. Again, because I don't care what's happening on the left-hand side, I'm only concerned about what's happening on the right-hand side. So when I look at my function, I trace it along, and I say, okay, as I get closer to 0, I see that my graph is kind of just getting out of control. I see that it's just continuing to increase without bound. So what I would be able to say is, once again, I think my limit does not exist. There's not a single value that I can say actually works or would be a good guess for what we would get if we have an input of 0. Or again, if you wanted to say it looks like it's approaching positive infinity, that would be okay as well. Now, what do we do about this overall limit? Because it looks like our limit would be infinity. Well, if your left and right side limit don't actually approach a value, then you're just always going to say that that limit does not exist. So for the overall limit, we're just going to say it doesn't exist. We don't want to put infinity there for our overall value. I mean, some textbooks might say that, but a more widely accepted thing is going to be to use does not exist. And then finally, let's go ahead and evaluate. So if I wanted to evaluate f of 0, I have to figure out what do I get when I plug in 0. And guys, if you go back to the function, if I plug in 0, I get 1 over 0 squared, which just ends up being 1 over 0. We know that that's undefined. So if I ask you to find the actual value for your function, it is undefined. Okay, last one. Once again, I'm going to pause the video, fill in the graph, fill in the table, come back, and we'll talk about the limit. All right, so last one. So when we look at this, again, we're going to look at the left side limit and the right side limit, and then determine from there what we'll say about the overall limit. So let's use the table for the left side limit this time. I'm sorry, the graph for the left side limit this time. So if I want to find what is the limit as x approaches 0 from the left, I'm going to need to cover up the right side of my graph and look at following that function. As I get closer to x equals 0, can I make a guess about what my output might be? And once again, I notice that my function is just decreasing without bound. Like it doesn't look like it's going to reach a specific value. So there's two ways I can write that limit. On the left side limit, I could either say that the limit does not exist if you don't want to worry about whether you have to write infinity or negative infinity, or because it is approaching what looks like it's going to be negative infinity, I could write that for my left side limit as well. Okay, then on the right side, let's use the table. So I'm going to cover up the left side of my table because I'm only concerned about what's happening on the right. Okay, and then I look at what's happening with these values as my outputs, and I start to notice, hey, those values are just getting larger, and it seems like they're not really approaching any one value. So once again, I would say, okay, it looks like this limit does not exist. So I would write either does not exist, or I could say, it kind of looks like those numbers are just continuing to get larger and larger and larger, and they're positive. So it's increasing without bound. It's going towards positive infinity. So I could write that as my limit as well. Now remember, we only do negative infinity or positive infinity if we're talking about the left side limit or the right side limit by themselves. When I look at that overall limit, if there's a does not exist, that's going to be what my overall limit is. Okay, so I'm just going to say does not exist for my overall limit because I can't really, first of all, there's two different infinities it's approaching. So it's not even approaching the same infinity. But secondly, when we talk about the overall limits, we are saying we need an actual value, not an infinity. So we would say does not exist. And then finally, evaluating this function when f equals 0. Again, if I try to put 0 in for x, I just get 1 over 0, which is just 1 over 0, which is undefined. All right, that's it. Let us know if you have any questions, and we'll see you in class.